Okay, we are back again to the practice questions for CLEP Calculus that I downloaded from here. Link should also be in the description, and we are going to go straight back to where we left off. Here's number 39. Let me grab another piece of paper here. So we have f is the function defined by negative 3 over x squared plus 4 over x cubed with the domain x equals 0. So we're only considering positive values of x. We're not worried about negative values of x. And what is the minimum value of f where x is greater than 0? So we need to find the derivative and then find where that derivative is equal to 0. And then we're just going to assume that that is a minimum because that's what it asks us for, at least for positive values. So it told us 3 over x squared plus 4 over x cubed. And of course, to do derivative stuff with this, we need to rewrite the exponents to get them to be not fractions. So negative 3 times x to the negative 2 plus 4 times x to the negative 3. And we're going to take the derivative of this in the normal way, where we bring the exponent down, multiply it with the number that's already there. So negative 3 times the negative 2 is positive 6. And we are going to subtract 1 from the exponent. Negative 2 minus 1 is a negative 3. And then we are going to bring that exponent down. Negative 3 times the 4 is a negative 12. So we are subtracting 12x. Negative 3 minus 1 is an exponent of negative 4. So that is your derivative. And just for simplicity, again, ease of what we have to do, we can pull out some factors. So we can say 6 times x to the negative 3 pulls out entirely, so we have 1, and that leaves behind a 2 times x to the negative 1. And we're going to rewrite this back to something a little more familiar for convenience. So 6 over x to the third times 1 minus 2 over x. And now we are asking, where does that equal 0? And obviously it could be, well, it couldn't be 0. And that would give us a divided by 0. And x only where x is greater than 0, not where x actually is 0. So we can't make any 0 out of this portion, but we can make a 0 over here. We have 1 minus 2 over x. So if we make x equals 2, then we get 2 over 2 is 1. 1 minus 1 is 0. And then the rest doesn't matter because you're multiplying by the 0. So we say that we are looking for things where x equals 2. And then we are going to feed that back into the original equation. So again, it's negative 3 over 2 squared plus 4 over 2 to the third. And that equals negative 3/4 plus 4 over 8. And we have to properly add these, we need to make a common denominator. So we'll take the 3/4, multiply the top and the bottom by 2. So we have a negative 6/8 plus 4/8. Negative 6 plus 4 over 8 equals negative 2 over 8. And that equals, bring it back to a simpler form, equals a negative quarter. And that is the answer, so we can put in negative 1 over 4. And that is the answer. So it's fairly straightforward, just with the twists of dealing with those exponents under the fraction, and we have to move them in and out in order to deal with things more easily. All right, number 40. If f is a continuous function such that the definite integral from 0 to 2 is 6, then the definite integral from 0 to 1 of the f of 2t equals what? So what we notice here is we are doubling the variable and then having the distance of the integral. So what is that? What are we actually talking about when we have f of t, let's say f of x, versus f of 2x? So if we have, let's just do a simple y equals x. Now if we say, if we take the function and we're putting in 2x, that means that for whatever x value you have, the y value that you're going to get is the y value from 2x. So the y value of 2x is that one. So you're actually going to get a value there. And, you know, you can do that for each one. And basically whatever that function is, you're taking it and you're squishing it in, right? You know, if it's some kind of curve, it's going to be the same curve, just squished in to a smaller space, because you're going through it twice as fast, because you're doing, instead of the x, you're doing the 2x. So you're taking the y values that should be out here and bringing them in here, because you're for each x value you're taking the function value of the function for double that x value, but at the original x coordinate. So everything is being moved in by a factor of 2. Everything is half as narrow, and that's why we're getting from 0 to 2 instead of 0 to 1. It's the whole thing, like in this, 0, 1, and 2. So whatever that is, it's just being squished in to be at the 1. So the shape of the function, we don't know what the function is. It's a mystery function f. But the shape of it is the same. It's just squished into half the space. And we're only, that's the space going from 0 to 2 being squished into 0 to 1. So that's the exact same shape, just squished. And because it's been squished in half, or squished by half, then we can take a fairly good guess that the area is also squished by half. So we take that 6, and it's squished by a half. Half of 6 is 3, and that's B, and that is the answer. So, it's one of those where there's not really a lot of actual math involved so much as you just have to recognize what the notation is telling you, and then you would intuitively know, okay, we're talking about squishing the function by the factor of a half, because that's not something, usually it's just a function of some variable. So when we're talking a function of something being done to that variable, that's transformation of the original function in some way. And again, because you're multiplying it by 2, you're taking whatever is out there and bringing it in. At whatever, at the same x coordinate, but the y coordinate for what double that x coordinate would have been. So it's just being squished in. So that's how that kind of thing is done. Okay, number 41. Let f be the function that is 2x cubed. Let's the middle of the screen a little bit. Minus 27x squared. The slope of the line tangent to the graph, so meaning the derivative at x equals 2 equals the slope of the line tangent to the graph, again, just the derivative at some k, which is not 2. So what is the value k? So we're saying that whatever the slope or whatever the derivative is at x equals 2, there is somewhere else on the graph some other x value that has the same slope. And what is that x value? Right, so let's think I can do it in this space here. So we have the 2x cubed minus 27x squared, and again, straightforward power rule, derivative, bring the 3 down, times the 2 is 6, x, 3 minus 1 is 2, and we're subtracting, bring the 2 down, multiply by the 27. 27 times 2 is 54, 40 plus 14. And 2 minus 1 leaves you with x to the first power. Okay. And just for little easiness, again, we can do a factor here. So we can pull out a 6x, and that leaves us with x minus 7, or 6x times x minus, not 7, 9. 6 times 9 is 54. Hello. What is that, second grade math? 6 times 9, okay. So we also know that the, what is that slope? What is that slope that we're doing the at x equals 2, right? So 6 times 2 times 2 minus 9. So we have, 12 times negative 7. And that becomes negative 84. Right, so now we want to know we have to solve where is the other place where the other x value where that equals negative 84. Where is negative 84 equal to 6x squared minus 54x? And to do that, we have to bring the 84 over. 6x squared minus 54x plus 84. And what we're going to do to help with that is we're going to factor out the 6. So we just have the x squared. We have minus 9. Remember, it was a 9 that we multiplied with the 6 to get the 54. X plus, and the 84, remember we got 12 times 7 to get the 84. 12 divided by 6 is 2, so 2 times 7 times 6 is 84. If we get rid of the 6, we're just left with 2 times 7, so that's 14. So that simplifies to that. And again, you could do quadratic equation, whatever, but we've simplified this enough that we can factor it. So x, what multiplies to 14 but adds to negative 9, and we think that is negative 2 and negative 7, right? 2 and 7 make 14. 2 and 7 add to 9. So negative 2 and negative 7. It takes a little bit of thought sometimes, but still within the bounds of what you can do fairly quickly. So that slope occurs at x equals 2, which we already know, and x equals 7. So, it already told us that it's not 2, and of course 2 was the given. It's just telling us it's not in the same place twice, but we fill in 7 because that is the answer. So we have to go out to the slope, what the slope is, and then work backwards to find out where else that slope occurs by solving for x. And after a little bit of work, we can get to the 7. Okay, moving on. Next page. Okay, number 42. Let f be the function, so our function is x over the sine of x. And which of the following statements are true? We only have 3 options instead of 5. Isn't that fun? So yes, key point, indicate all such statements. So it's not which one is true, it's which of each of them are true. I don't know how this would necessarily be represented in terms of filling in the blank or stating the answer, but it's open, and it's like a fill in the box where you fill in the number in the box. It's going to be, you can say whatever you're going to say. You're not just limited to A, B, or C. But again, as we usually do, let's examine all of them by themselves. So for A, we're asking about the limit as x approaches 0. So for A, as you get close to 0, you would have, that would be 0 over the sine of 0. And, again, remember we're talking about the unit circle, and the sine of theta is the y. So we have the 0, we have the pi, we have the half pi, and at the angle of 0, that's over here, that's right here, where the x value is 1, but the y value is 0. So at the sine of 0, the value is 0, and that's just 0 over 0. So that's not valid. That's not a value, but that's why they're asking us the limit as x approaches 0, not where x equals 0. And because it's the same thing over the same thing, it's a fairly good guess. Well, also because when you're talking the unit circle here, if we kind of zoom in, on that, let's talk about a very, very, very small x as x is getting close to 0, right? So where x is the angle, the angle is the x, and then the sine of, well, let's just write a theta as the angle. So as theta approaches 0, very, very small theta, very small angle, the angle being the arc length along here, and then the sine of theta equals the y, which would be whatever that is there, and I kind of drew it poorly, but you can see that for the very, very small angles, the arc length and the y value are pretty darn close to the same thing. I mean, that's definitely approaching going to be the same. As it gets smaller and smaller and smaller, it's approaching the same thing right until the point where both of them actually become 0, and it becomes a divide by 0 and an invalid number. So is that equal to 1 as that limit goes there? I think we can pretty confidently say yes, that one is true. So then as the angle approaches half pi, so b half pi over the sine of half pi. And again, on our unit circle, at the angle of half pi, you're just up here, where the x value is 0 and the y value is the 1. So sine of half pi just becomes 1. So half pi over 1 just becomes half pi. So that's not even a limit problem. At x equals half pi, the function literally is half pi. It's a valid value there. No divide by 0 anything. And then as the angle approaches pi, so we're talking going all the way over here, and you're getting the same thing where the sine of pi would be 0, because you'd be at a y value of 0. But you have the pi on top, and it's kind of the reverse of this, but also it's not, because as you're approaching 0, the angle, the theta, is getting close to pi, while what's underneath is getting close to 0. And as you get close to 0, if you're actually dividing by a larger number, dividing by something very, very close to 0 makes it very, very large. With this side, it was something small, and you could see they were very, very close to each other. But if you flip that over, it's getting large. I'd have to graph that out, but I suspect it's going to infinity at that point. But it's definitely not the same situation on the other side, because you're dealing with a non-zero value of that angle. So that's false. And so the answer for 42 is A and B. A and B are true, C is false. So that's that one. Okay. And here is 44. And we have seen this one before, but if you remember the last time we saw it, the picture was messed up. We had that little bit in the middle, but those lines weren't there. That little bit was all we saw, and I said, I have no idea what's going on here, and we made some good guesses, but now we can talk about this problem as it was actually intended. So let's go over it again. F is some continuous function. This shows the derivative of that function, and what is happening here. So we have the slope that is positive. So the function is going up, but it's decreasing. So it's flattening out as we go. Let me draw a quick little picture. It's positive, but it's kind of flattening out as you go. And then right at the x equals 2, x equals 2, it hits a slope of 1, so just straight up slope of 1. And then at that x value of 2, it suddenly switches from the slope of 1 to a slope of -1. So it turns a very sharp corner, right? And then it continues downward with a negative slope, but an increasingly negative downward slope. So it keeps going down, and it's kind of pointed at the top and more rapidly dropping off to either side. So like we had before with the infinite slope asymptotes, where it was going full vertical, because you have a jump in the value, you are turning a sharp corner, and this would be what you traditionally call non-differentiable, because it is not a smooth slope, it is a slope that jumps, right? So you couldn't do a proper equation. You could do a piecemeal equation, but you couldn't do one equation that covers that whole thing. That's why we're showing that jump in that graph. So which of the following statements is false? Is the function at x equals 2 minus the value of the function at f equals 0, is that greater than 0? So we don't know where this is vertically, but we can certainly say that at x equals 2, it's at a maximum, and at x equals 0, that's more down here, that's a smaller number. So the bigger number versus the smaller number is definitely greater than 0. So A is a true statement. Is the function defined at x equals 2? It is. It has some value. The slope is turning a corner there. You can't say what the slope is at x equals 2, because it does that rapid. It's got that point. So the slope exactly there isn't really anything. It's anything and everything. But the actual value, it does come to some actual value where the slope turns the corner. We don't know where that value is, because we don't know, we don't have a vertical reference, but we can say it's defined. So f is differentiable at x equals 2. So I had jumped ahead of myself. I was just saying we cannot find the slope. We cannot get a smooth derivative. It's a piecewise graph, the slope there, and therefore the derivative is not anything. It's anything and everything. So that is not properly differentiable. So C is a false statement, and that is indeed the correct answer, but let's go through the rest just to satisfy ourselves. F has a relative maximum at x equals 2, and in fact it definitely does, because the slope is positive and then the slope is negative. Normally when we see a relative maximum, we see the derivative crossing 0 smoothly, and this one crosses 0 with that jump, but it is crossing 0 nonetheless. It is going from positive to negative without ever touching 0. It's why we get a point instead of a smooth curve, but that is definitely a maximum because the graph is switching from going up to going down. And then for E, F is decreasing from the range of values from x equals 2 onward to infinity. And we can see that because from 2 onward to infinity, the slope, the derivative, the slope is negative, which means it is decreasing, it is going down. So that is also a true statement. The lone false statement is C, and that was the answer. And we will pick up from there in the next video.